Okay, from now on it's all downhill. So what I'd like to do, before I even start, is to tell you that even though Professor Grossberg and Mr. Rubinstein asked me to give a few talks on hydrodynamics, in fact the subject is so big that they have had summer schools exclusively devoted to the topic. So a very good resource is in fact the set of notes from 2011, where the whole month was spent on hydrodynamics. So I strongly urge you to essentially go to the website, maybe not now, but this evening and tomorrow, and take a look at both the notes and the lectures, which I think are videotaped and available to you for 2011. So the whole subject is very large, and what I'd like to do in the next 3 lectures, one today and 2 tomorrow, is to give you a flavor of the subject by basically working out a few examples. But before that, I have to also tell you a little bit about the equations and see how and where we essentially can derive them. In order to do that, I'm going to use a lot of analogy and comparison, because this is not a summer school on hydrodynamics, it's a summer school on polymer physics, physics of matter, and biological physics. And so the real question is, where does hydrodynamics fit in all this? And you already heard people mention this. And let me give you my view. So I'm going to go between Power Keynote or PDF and the Blackboard. So please stop me, as Phil already said, stop him, stop me as well, whenever you don't agree, whenever you're confused, whenever I'm wrong, whenever all 3 are true. If I look at, it's already dead, so I don't think I'm going to use this, but maybe there's a physical version of this. Okay, so what Phil told us about an hour and a half ago or so is trying to understand the basic interactions in matter, thinking about what happens at the level of not just initially starting with just a couple of pieces of matter, a couple of particles, but eventually the goal is to look at what happens if I have a large number of elements which are interacting with each other, and that's the subject of, if you like, thermodynamics in the 19th century, and in the 20th century, and continuing the subject of statistical mechanics, and how you essentially start thinking about what happens at the level of individual particles, and then move to the scale of what happens when I have a very large number of particles. And I want to say this because I want to contrast this, if I might be allowed to, with what hydrodynamics does, which is to start from here, but also do a little more of a coarse graining, not only in thinking about a large number of particles which interact with each other, but also starting to ask questions about how things vary in space and how things vary in time, where I'm thinking about understanding how, given interactions between particles at the microscopic scale, what can I say by coarse graining and asking questions on length scales much larger than the length scales over which the particles interact, and on time scales which are much larger than the time scale on which individual particles interact. Of course, that immediately suggests that there is a comparison, and in fact, the whole subject of hydrodynamics, in some sense or the other, can be thought of as associated with comparison. Comparing terms and equations, comparing energies, comparing time scales, comparing length scales. And in a sense, that's it. The whole subject revolves around this idea, but that's easier said than done. And the reason it's easier said than done is because as soon as you have to start comparing, you've got to ask, what are you comparing with? What is the microscopic scale? Is it the particle size? Is it the distance between particles? If I'm thinking about a polymer, is it the pore size? If I'm thinking about a network, is it the size of the holes in between? Is it the distance between crosslinks? So you have an enormous richness of physics simply associated with asking what I choose to be the scale or scales on the microscopic length, on the microscopic domain, and on what scales am I averaging. In other words, which interactions am I keeping and which interactions am I dropping out. And that's why this subject is very rich, and that's why it's also very difficult. And exactly the same way as you think about microscopic length scales, you've got to ask about microscopic time scales. Phil told us about understanding or thinking about what happens when you have particles hopping over wells. You can think about particles, or not particles, but extended particles like polymers relaxing. And again, each one of these has a microscopic basis, and I want to ask, when I keep or not events associated with microscopic basis, and then look at time scales much larger than that, how do we average? There are 3 ways to do this. at least. If I want to try and write down theories on long length scales and on long time scales, I can start with a microscopic picture, assuming that I understand it at some level, and then I somehow coarse grain. I systematically average. For example, I'm going to show you the hydrodynamic equations in a little while, even though they were written down by Navier and Stokes 150, 170 years ago, more or less phenomenologically, people since then, slightly more recently, 80, 90 years ago, started to derive them from a more microscopic theory using a Boltzmann-like approach, where you think about individual particles, think about how these particles collide with each other, understand how momentum is exchanged, and then try and average and understand what kinds of equations result. The advantage of that is you can be very rigorous. The disadvantage is it's very hard. And in fact, in most situations, it becomes particularly hard and almost impossible as soon as you go beyond the dilute limit. That's just because you just can't deal with the multiple interactions that happen. There is an alternative view, an older view, still very successful. And the older view is to say, I'm going to measure. I'm just going to go ahead and measure the properties of the liquid. I'm going to measure the properties of the soft material that I'm interested in. And I'm going to try and relate different things. And I'll come to that more precisely in a minute. And then, if I use that, I can then use these equations of state sometimes, or equations which are called constitutive equations, and then try and write down. I'm being vague over here. I hope I'll be precise in a little while. And this would be more of an empirical approach. That's the approach which was used and still is used, for example, in the engineering community. In biology, a lot of the time we are forced to do that just because we don't know enough. And then there's a more recent, much more beautiful way of doing this, which somehow goes in between these two, which is to use notions of symmetry, to use notions of invariance, which once you get used to them becomes intuitive, but the hardest thing is to get that intuition. And I want to try and do a little, give you a little bit of that through calculations. Okay? So we have these three pictures, and each one of these three pictures you essentially end up with something which looks similar. In some cases you know more, in other cases you have to measure from an experiment. And in each one of these problems, you essentially end up with scales which are, equations which I'm going to broadly call hydrodynamics. Why do we care? So there are also three reasons to care about hydrodynamics. Subject, as I said, which is very old. One reason is more or less obvious. There are lots of intrinsic physical problems of interest. The atmospheric motions right now around Denver and Boulder, not very pleasant. All the way to thinking about what's happening in my gut and yours are problems of fluid dynamics. There are mathematical reasons to think about it, because from the beginning, hydrodynamics was a very difficult subject, and so it's been a test bed for the development of tools. Unfortunately, I'm not going to be able to tell you a whole lot about those, because I'm going to use one tool repeatedly, but it's a very powerful tool, as you will see. And then there's a third reason, particularly in the context of, I think, the summer school, which is that hydrodynamics is a fabulous way to start developing analogies. And because you can develop analogies using hydrodynamics, if I understand how to do it in hydrodynamics, I can then maybe go ahead and use that as a way to understand how to develop theories for these new kinds of materials. Nobody did this better in the last 50 years, I think, than Duchenne. Basically, you use analogies based on what he knew, what others knew, and created theories for new things. So those are the three reasons to study it. And if I want to think about it, I have no choice but to start understanding how to write down differential equations. That's the language that I'm going to use all the time. And in order to do that, I have to first ask myself, what am I trying to relate? Okay? So this is extremely elementary, but I think still worth pointing out. I have to first worry about what the independent variables are. Okay? If I'm thinking about long wavelength and long time, so naturally I have to think about position and time. So space and time are my natural independent variables, but there's no limit to the number of dependent variables. For example, if I'm thinking about the gas in this room, I might be interested in the density of the gas, I might be interested in the concentration of individual constituents, I might be interested in the velocity as a function of space and time, I might be interested in the stress, which I will introduce in a little while. If I'm thinking about just a simple fluid, and it's not so simple, as I'll try and convince you, those three are sufficient. If I'm thinking about more complex kinds of matter, like the ones that we've already heard a little bit about, for example, this table, it's an elastic object, or it's a plastic object, or it can be some combination of those two. Again, I'll define those things in a while. I might have to worry not only about position, not only about velocity, but about position. In fact, we are taught in elementary school that the difference between a solid and a liquid, at least in the simplest setting, is associated with the fact that the solid resists changes in displacement, while the liquid does not resist changes in displacement, it only resists changes in the velocity. A very, very simple, very naive picture, which we will use. And everything in between, in some sense, is soft matter, including elasticity. Right? So all the zoology is associated with essentially asking, how do we build in a description, and the description can be done at different levels, of the order or the disorder in the system, which means the first and the hardest question in many of these problems is to try and understand what variables do I need to essentially track in order for me to be able to understand something about the system. So, if I have a crystal, it may be sufficient to think, a perfect crystal, it may be sufficient for me to think about just the displacement relative to the original position of the individual atoms. If I think about not a crystal, but a liquid crystal, so objects which you'll hear a lot more about, which have an orientational order, so they are long molecules, and these long molecules can move around in space, they can tumble, but they don't necessarily have a vector associated with them, because one end is the same as the other. So effectively, mathematically, you should think of them as objects where they have a symmetry with respect to rotation about their axis by pi. Okay? So they have an orientation. So I have to then track not only the displacement, but also the orientation. If I'm thinking about a magnet, then I have a magnetic field, I have a polarity, so I have to track these. And there is a huge community of scientists in condensed matter who worry about all the different parameters that you have to track, in the broad rubric under which they think about this is the notion of how do we essentially define the order parameter. So very hard, very important question right at the beginning is, what class of dependent variables do I need to essentially follow? I won't tell you anything more from now on about all the rest of these. You will spend the next 4 weeks thinking and learning about these. I will focus only on the density, and in fact even that will go away very quickly. I'll only think about the velocity and the stress for the rest of this. Because that's what defines a fluid, and I'll again be more precise as we move along. Not only do we have to worry about what the independent variables are, and also what the dependent variables are, I also have to make a choice, because things are varying in space and time. I have to make a choice as to how do I track them. Do I track them by being a little animal which runs with parcels of fluid? For example, if I'm thinking about a mixing problem, somebody introduces a noxious chemical, I could go along with that little blob and understand how that blob moves in space and time, which makes a lot of sense. Or I could just decide I'm going to sit in a frame attached to the lab and ask how things move relative to me. Now, in principle, there's a very easy way to go from one to the other. I just jump on a frame, which tells me whether I'm moving at a particular velocity or not, and then I'm allowed to do that. But in practice, choosing frames is extremely important, because it sometimes allows the problem to become simpler. In fact, the profound insight of Newton, in some sense, and solving the gravitational problem was to choose the correct frame. Okay? Rather than getting epicycloids and hypocycloids and so on and so forth, once you choose a frame which is attached to the center rather than attached to something which is moving, suddenly everything became simple. And so one can't, I think, underestimate the importance of both understanding what dependent variable to essentially, or set of dependent variables to pick, and what frames. And in hydrodynamics, there are two frames which are typically used depending on the kind of question. In fact, again, when I say hydrodynamics, I don't mean just limited to fluids, but just thinking about how things vary on large length scales and on long time scales. One is the material frame, jumping on the blob and trying to understand what happens. Jumping on a set of particles and understanding what happens. So that's called the material frame, because we're tracking materials. It's called the Lagrangian frame, even though it was actually written down already by Euler. Not clear to me why. There is another frame, because Euler has his name attached to so many things that perhaps it's good to split the credit. The Eulerian frame is a different frame where I just sit. That's me, lazy, sitting in front and watching what happens as things go past me. Okay? So that's more associated with an inertial or a lab-based, and typically in hydrodynamics it's useful, in fluid mechanics it's useful because fluids coming in, fluids leaving, and I don't really care so much about what happens outside the window that I'm interested in. Again, next time I'll actually...
The Lagrangian frames are then meant to be inertial, well, or they could be accelerating?
Okay, so I write down inertial or non-inertial, but again, it's a choice that we have to make. I'll give you an example, which again in elementary mechanics we learn, Euler's equation for the rigid body. Never mind even something like a fluid which is deformable. I can write down Euler's equations for a rigid body in a lab frame, and then it's a headache because the moments of inertia are continuously changing with respect to the lab frame. But as soon as I jump onto the body frame, the moments of inertia become constant. So it depends enormously on what you're trying to do, and how you do this then determines or leads to what frame you pick. So atmospheric sciences, hydrodynamics on the scale of the planet, you're always using a non-inertial frame. And the reason is because you're sitting on Earth, and I'm not really interested in doing everything with respect to a fixed frame on a star, because it's meaningless since all the experiments are being done in that rotating frame. So I can't give you an answer beyond it depends on the question. Okay, so I have to choose frames, and I'll go back and forth through examples in a minute. And once I've chosen the frame, so I have my independent variables, I have my dependent variables, I may have to choose different frames depending on what I want to do. I have to write down some laws. I have to write down what those coarse-grained average laws which I talked about are, and just as importantly, I have to tell you what the boundaries are and what happens with the boundaries. Extremely important that I don't ignore that. Again, we'll come to that with hydrodynamics. There's a very simple boundary condition which is the source of every nightmare in the subject. And that's the boundary condition associated with the fact that if the fluid is flowing past any rigid object, then the fluid is supposed to be stuck. And I say supposed to be, because I'll tell you lots of places where it's not true. But this has been driving the subject for 150 years. Okay. If I have the laws and the boundary conditions, that's in some sense where the physics ends. But in fact, I'll claim that in fact that's where the physics starts. Okay? And that's the reason that I think you're all here, because this whole subject is so beautiful, because even if we know the laws and we've known them for 150 years, there is essentially no limit to the richness of phenomena. And that's really just focusing on understanding the consequence of very, very simple laws. How do we understand them? We could understand them quantitatively through solutions, numerical, analytical, and so on. We could understand them by basically comparing terms, already like what Phil taught us an hour and a half ago. And the next three lectures today, tomorrow morning and tomorrow afternoon, what I want to do is to essentially walk you through the laws, try and tell you something about analogies to different fields, tell you a very simple set of solutions. I have no way to show you how to think about the problem except by solving problems. I just don't know any other way. There is no general theory beyond the theory associated with the laws themselves. After that, it's grunge work. Okay? It's very beautiful because you can compare with the experiment quickly. You can't hide it. Today on the balanced laws, tomorrow on understanding a very fundamental idea which started in hydrodynamics but now pervades all of physics, which is the notion of stability or instability. If I start with a system, be they particles next to each other, be they planets revolving around the sun, whatever. If I start with that, does it stay that way? Very simple question. How do we understand stability and instability? And I'll tell you a little bit about that, both in the context of things close to the threshold. If I start a ball close to the top of a hill, it will run away. If it's close to the bottom, it will stay there. So close to a stable point, close to an unstable point, and what happens far away? And the most beautiful example of what happens far away from the onset of instability is, of course, turbulence. Fundamentally still an open question. I'll tell you little snippets of what we've understood over the last 60 years or so. And then on tomorrow afternoon, and then I'll show you how to solve a few other problems. And tomorrow afternoon, I'll start switching towards not just simple fluids, but slightly more complex fluids. Sponges, for example, the kinds of things, or bath towels, the kinds of things that you use in the morning and you use again tomorrow. To wash yourself and to wash the sink. Okay. All right, so I'm going to tell you about laws. There are many ways to write the laws. So far only words. Okay? One way to write the laws are in terms of what happens to small elements. And already there is an assumption that inherently you have to make, because those elements have to be small compared to the size of the system, but large compared to, for example, the particle size, or for example, the distance between particles, or ideally both. Okay? So already in your mind you have to have, even if you've not thought about how to do it mathematically, a conceptual issue, which is on what scale do I essentially write down these? And that then tells you how many independent and dependent variables I have. That would lead to laws in differential form, a form which essentially allows you to write down everything in terms of differential equations. But there is an alternative view, and I don't think I'll have time to essentially tell you about that, so I'll just quickly indicate that. The alternative view is to not write them down in terms of local quantities, but in terms of non-local quantities. Okay? You will hear, I think, later on something about molecular motors and so on. I think Fred McIntosh perhaps is giving talks on that. So let me give you an analogy. Not using molecular motors, but using traffic. Okay, so cars come into a highway, they move, then they leave. Once they're in the highway, if I look at a length scale which is large compared to an individual car or the distance between cars, but small compared to the size of the entire freeway that I'm looking at, I can ask what happens now to the cars rather than by following individually, the cars following them as their density, the number of cars per unit length. And you clearly know that what happens often is that I get traffic jams. So what's the definition of a traffic jam? A large number of cars at a particular location. The density becomes large, but the density is not becoming infinite. What's actually much more interesting is the gradient in the density. Okay. So if the gradient in the density starts to become large, and condensed matter is a great example of that, when essentially you have a switch between a gas and a liquid, or a liquid and a solid, some quantity, a gradient in the density, for example, is changing very, very quickly. And so you may not be interested in thinking just about what happens to the gradient of the density, but I'm just interested in understanding how things move in, how the cars move in through the shop and move out on the other side of the shop. In that case, I don't really care about the details. I'm interested in an integrated form. And an integrated form is actually a much more powerful way in some sense because it doesn't require that much differentiability, which you might have thought from your mathematics classes is sort of a technical detail, but it isn't. Okay. Do you require that much differentiability? I won't say more than that because it will take me too far away. But you have to make a choice. You have to make a choice whether you want to write down the equations in their differential form or their integral form. And for those of you who do computations, often it's very useful to write them down in their integral form. Okay? And the reason is that you don't have difficulties numerically. All right, so on to business now, on to the equations themselves. First thing, I have to conserve mass. Or even if I don't conserve mass, I have to know how much I don't conserve mass. Okay? So I have a density of a single component fluid. If I have multiple components, I just have more equations for each component. Conservation of mass simply says, physically, that if I have a density of fluid, and I think of a parcel, which I'm looking at now in the frame attached to the lab, then why will that density change? It will either change because I have local changes, so density changes locally, or because material is coming out at a rate which is different from the material going away. That's it. Those are the only two ways in which density can change. Either the particles are moving apart or coming together, or particles come in at a rate which is different from the rate particles come out. Okay? If I have a third agent which is dumping particles, or I have reproduction or something like that internally, we'll have to worry about that as well. I'll tell you in a minute. But that's it. And conservation then says that in this lab frame, the rate of change of density is simply associated for compressible and incompressible, it doesn't matter, is simply associated with the rate at which material is moving in and the difference between that and the rate at which material is moving out, which you know from your elementary calculus is just a divergence. But the divergence operator simply tells you about how much increase or decrease in flux you have at a particular location. Okay? That's it. So this is telling you about conservation of mass. If I now, in addition, had new species associated with reproduction, in biology, for example, extinction and so on, all that will be associated with the right-hand side. That's conservation of mass in a lab frame. If I expand out that second term, divergence of rho times u is grad rho times u, and then a u operating on divergence of u operating on rho. And so if I just write down the two terms, I can write down this same equation, the left side of that equation, as dt rho plus u dot grad rho plus rho times divergence of u, and I've moved rho times divergence of u to the right side. The reason I've done that is because now the left side has a very nice and very simple interpretation. I just use the chain rule. So if I track particles, so now I'm tracking particles. I'm not now sitting in a lab frame. If I track particles, the total derivative is the partial derivative, and I'm sometimes going to use a subscript and sometimes I'm going to use 0 dt, but subscript always means partial derivative, and then I have essentially dr dt times the spatial derivative. Just use the chain rule. Okay? Nothing more than the chain rule. So far, I've not said what dr by dt is. As soon as I say dr by dt is the flow velocity itself, now what I'm doing, so suppose I say this is the flow velocity. So this is just a definition of total derivative. I've said nothing about anything so far. But as soon as I say this is the flow velocity, then the notation that people use, both in mathematics and in physics, is that this becomes now the material derivative, because it's the derivative with respect to a parcel that's essentially moving at a velocity which is the flow velocity itself. And so I can write down my conservation equation rather than in a lab frame, in a material, in a Lagrangian frame, like d rho by dt is minus rho times divergence of u. And again, it has a very nice interpretation. It says that if I'm now running with this blob of fluid, then the rate at which the density is changing is simply associated with the divergence of velocity in or out times the density. Okay? Why and when this is useful, you will see. You will see because it allows you to write down when quantities may or may not be constant, may or may not be conserved. Again, I'm doing this in the most general case, but in fact, for most of what we will hear, I think over this summer, here you basically have a situation where you think about materials, fluids which are incompressible. If they're incompressible, that means the density doesn't change, and the density doesn't change with respect to a frame where I'm moving with the particles, and if that's true, then naturally it follows that divergence of u is equal to 0. Okay? This is a very hard constraint. It's a hard constraint because it's not a differential equation which is telling you how things change in time. So it must be true always. It's not telling you how things relax. That's the one source of difficulty in all these problems in hydrodynamics. That source of difficulty is associated with the fact that this essentially allows some sort of non-locality. Okay? What is the physical variable that forces this non-locality? It's the pressure. If you guys remember your calculus of variations, you remember that every time I have a constraint, I have a Lagrange multiplier which enforces the constraint. And so the pressure, if you like, is the Lagrange multiplier which enforces the constraint of incompressibility. Okay? So, and there is a duality, again, which is worth pointing out. And the duality is the duality between constraints and constitutive equations. Every time I have a constraint, I switch off, because the constraint essentially forces certain things to be true forever. I switch off an equation of state. As soon as I have incompressibility, the pressure you can't essentially write down as a function of density and temperature. You don't have that freedom. Otherwise, I'm over-specifying things. And I'm going to now introduce a subtlety in a little bit, because the pressure itself has multiple interpretations. We just heard about an osmotic stress, but I also have a hydrodynamic stress. And hydrodynamic stress has a pressure, and the osmotic stress, and isotropic has a pressure. And the two are different things. But in one limit, you can't distinguish between them, and I'll tell you about that. Okay, that's conservation of mass. Well, I have to conserve mass, I have to conserve momentum, I have to conserve energy. How can I write down equations for conservation of momentum? Well, I'll start with Newton's laws for particles. Newton's laws for particles, again, that's why I now am allowed to, I'm going to think about moving with particles. If I'm thinking about moving with particles, rho is the specific density. Okay, there's no interaction at all between the particles, and the particles simply accelerate and decelerate because of external forces. So rho times du dt, and I've deliberately written down this material derivative because I'm running with the particles, is the external force. But now it's not a force, it's a force per unit volume because everything's written down not for mass, it's written down for density. All the devil is in that term. And that term, again, has a divergence form. What is that divergence form? That's telling you that if I'm now moving with this particle, which is accelerating or decelerating or set of particles, there are also interactions inside. And those interactions inside cause also changes in the momentum. Okay? And that change in momentum is associated with the internal interactions between the particles, and the internal interactions between the particles, again, it has to have this divergence form. It has to have it because I don't care about what happens. All external forces have already been taken into account. So therefore, the only thing that matters for this lump of particles which I'm tracking are the force imbalance from the boundary, which is exactly what will be written down in the divergence form. Everybody with me? Physically? Okay? No? All right. I'm going to stop now and I'll force you to ask me questions. I mean, so far it's words. Yeah, please.
Well, according to the lecture of Phil, I'm actually waiting for some numbers.
I will give you numbers. Yeah. So far, it's so general that I haven't told you whether it's a fluid or a solid. If you wait, I will. All right? So there are two approaches. One is start with specific problems, but I'm deliberately taking this other approach because you will see over the next 4 weeks specific problems. Okay? So forgive me for another 5 minutes. Question at the back.
So by material derivative you mean Lagrangian?
Yeah, exactly. Yes, sorry. I said that. I want to emphasize. The material derivative is exactly this frame that I move to when I'm running with the particles.
But it's also interesting that the Eulerian equation looks like the Lagrangian.
They're the same. It's just a question of what is my independent variable. Okay, in one case R is fixed in the lab and I'm just looking and trying to see how things happen with respect to a lab frame. In the other case I'm running with the particles. That's why I wrote down over here R is now a function of t, so I'm essentially running with the particles.
So is density constant? What's the
When I've written down over here, as I've written down over here, density is not a constant.
So what does incompressible mean?
Sorry, so incompressible deliberately means that d rho by dt is 0 and therefore divergence of u is equal to 0. That's incompressibility. This is saying nothing about compressibility or incompressibility because rho can be a function of space and time.
So are you assuming that the velocity of the flux is constant?
I'm not assuming nothing. I'm simply counting. So that's very important.
That looks like again like a Taylor series expansion.
No. This is not Taylor series. This is just a chain rule. D rho by dt is d rho by dt, the independent variable, and then d rho by dr, which is grad rho, and then dr by dt. This is an identity.
What I was thinking is, what if you have particles like they are evaporating, like they are accelerating and losing
accelerations and so on, I don't really care, because all I'm doing is counting mass. When you start telling me about accelerations and rotations and so on, that's associated with forces. So I think this is, maybe if nothing else, this is, I hope this is a lecture in hygiene, mathematical hygiene. You just have to count properly first. Okay? Because if I don't count properly, I'm not sure I have enough equations. And then I'll worry about whether it's a fluid or a solid or a gas or whatever. Because the important and essential thing I want to point out is this is as generic as possible. No assumptions. I'm just counting. First, I'm going to count mass. Then I'm going to count force. Then I'm going to count torque. Then, if I want, I can count energy, entropy. You tell me how many things you want to count. And all I'm doing is just writing down the consequence of counting. There's no physics so far.
There is, I think, an assumption, and there is physics, which is the fact that conservation is local conservation.
Very good. Yes, indeed. Yes. And I'm going to tell you what would happen if I didn't have that. Thank you. Sure, you're absolutely right. So I have, yeah, absolutely. That's why I said that I have a possibility of writing down a non-local form as well, indeed. Yeah, more questions.
This change in velocity independent of the orientation of the particles?
Okay, very good. If I'm thinking, so far for mass I don't care. Over here, we're asking a very, very subtle question, which is This is velocity translationally. So I'm following particles. I'm either following particles by following them literally in a material Lagrangian frame, or I could just sit in the lab and watch them. Now you're saying, what about orientation? Well, orientation is a different degree of freedom. Because if I have a particle, the particle could have a velocity, then it could have an angular velocity, and I could change them independently. So I have to separately count what happens to angular velocity or orientation, and separately count what happens to linear. So this comes back also to Shura's question. How many things do I need to count? And this is a question that you've got to ask before and after you try and answer every question. There was a question in the back as well. Yeah?
So this expression for incompressibility of fluid, why do you assume material derivative equals 0 and not the earlier derivative?
Not the?
So why do you assume material derivative equals 0, not the one on the left? Like just 0 dt.
This,
No, one line below, incompressible fluid.
yeah, these are equivalent.
Yeah, that's true, but you assume material derivative
Correct.
equals 0. Why don't you assume earlier derivative to be equal to 0?
Oh, the Eulerian derivative is always 0. I'm not saying anything about how the density is changing or not.
Why not 0 dt, partial derivative, not the capital?
Because I can change the density by essentially stuffing things on one side and taking them out of the other in a different way.
I guess the answer is it just doesn't matter. You could have assumed the partial derivative equal to 0 and then rho is constant. And then
If rho is constant, yeah, exactly.
Yeah, but that's the assumption.
But rho is constant only in a material frame. Rho,
No, but in general, that's the assumption of incompressibility, I guess, that rho is
Yeah,
constant everywhere.
if rho is constant
Frame,
indeed,
in any frame,
exactly,
in any
yeah,
frame.
yeah, exactly.
So partial derivative is also 0, isn't it?
Indeed. Yep. Because partial rho, and then you pull the rho out and you just get divergence of u is equal to 0. You get the same thing, yeah.
I'm a bit confused about the right-hand side. So if I'm sitting on the particle, why u is not 0?
I'm not sitting on a single particle. I'm thinking about a blob. Remember that this is not tracking single particles. I'm thinking about, remember the continuum approximation says that I have followed, or I am following a blob which is larger than the smallest particle that's there, but smaller than the system size. So I can have flux of particles in and out. Of course, I've not written down the formalism in terms of what the size of the blob is. So what you're really saying is, in fact, if I really wanted to do this properly, I have to also worry about what scale I'm averaging on, and there could be other terms. And in fact, in momentum equations, there will be. In the mass, there isn't. Okay, yeah?
Maybe another question to comment on this. How rigorous is that the current that appears in that divergence is really rho times u? Or rather than you should write more generally just the current and then write.
Thank you. Yeah. So I write down the current and then I have to write down what contributions are to the current.
Right.
Okay, but for single species, this is it.
But is it just by definition you can always write as rho times u? The current that appears in the continuity, mass continuity equation.
Yeah, because the current is just the amount of material which is moving in at a velocity u, so it's the density multiplied by the velocity.
By definition.
Yeah, by definition. Okay, if this was, is this a conservation of mass? What about conservation of momentum? I told you that I have this term, and I still haven't defined it. Okay, so I have an equation which is not closed, but the problem with this quantity is that if I think about the continuum picture, and I'm looking at it on a small scale, and I'm thinking about all the interactions inside associated with all the relative motions of the particles, liquid crystals, whatever they are, I have a problem. And I have a problem because I have to think about forces, but forces are vectors. And so I have to make sure that I basically have the ability to account for forces in all possible directions. Okay? And that's a problem because this equation is not written down, as I told you before, it's not written down for forces, it's written down for forces per unit volume. So, if I now write down forces per unit volume, this is a divergence, and I think I told you why it's a divergence, I'll say it again in a minute when I draw a picture, then I have a problem. That means this quantity must have dimensions of a force per unit area, a stress, but the problem is the force is a vector, the area is a vector. And I have a problem. How do I choose? In fact, I have to make sure that it's true for all possible things. So how do we do that? And I don't want to use a microscopic theory, I want to use a phenomenological theory. Deliberately, because it can then be adjusted to worry about different molecular microscopic theories. A way to do this, the cleanest way to do this actually is a very old way. It goes back to Cauchy. And let me try and explain this picture to you. So imagine that I have a volume which is small compared to the system size, but large compared to the individual particles, distance between individual particles. Okay? And now what I want to do is to try and calculate what this quantity, this stress is, which asks fundamentally the notion of what force would be present in this system at some arbitrary angle. The angle can be arbitrary, and therefore I must have forces which are also arbitrary. And I want to start with an equilibrium picture first, because understanding the dynamical picture is fairly easy. The equilibrium picture corresponds to essentially switching off the acceleration term completely. I may or may not have body forces. I can even switch off body forces. And if I switch off both, here is a very simple view of understanding what the stress is. What is the notion of a stress in a continuum theory? So this tetrahedron has an area of the face, which I'm going to call dA. That's the face in which I want to essentially calculate the force. So imagine that's inside your fluid, inside your polymer goop, inside a liquid crystal, whatever you want. So associated with that triangular face, there is a normal n, and there is no reason that the force will point in the same direction. A very important point. Very simple, but very important. Because the force can be in any direction, does not have to be in the normal direction. Okay? So the normal is n. The net force on this area is the stress, Tn, multiplied by the area dA. And if it's balanced, then that must be balanced by having the same, that force balanced on all three sides, the sum of forces on all the other three sides, associated with the three planes, which are orthogonal in this case, but you can generalize everything to non-orthogonal frames. Tn, the force on that face per unit area, multiplied by the area, must be balanced by T1, T2, E2, plus T3, E3, plus T1, E1. Okay? Elementary, just elementary mechanics. Multiplied in each case with the area, right? So that sum is associated with the double index. That's it. Once I do that, now I recognize that the area element itself is just the projection of the original area in the three directions. Okay? So dAi is just the normal to that tetrahedron times the projected onto the three different axes. These two together, so that means I can write down dAi like this, which means that this allows me generically to get around this conundrum, potential conundrum. I don't know how to write down the force on an arbitrary area unless you tell me the area, or equivalently, what Cauchy taught us is that in fact the force on an infinitesimal area, sometimes called attraction, is linearly related by the projection of a quantity which I'm going to now define called the stress times the normal. So the stress is a tensor now. It's a matrix if you like, if I'm thinking about Cartesian geometries, but it actually has all the correct invariances associated with tensors. It's a two-dimensional, two tensor, excuse me. So in 3 dimensions it will be a 3 by 3 matrix, and that matrix times a vector gives you a force. Okay? So all I've done is allow you to get a handle on this object, sigma, through its definition microscopically in terms of forces. Okay, question?
On the top of the three formulas, why does the left side has to be equal to the right side?
Oh, that's equilibrium. That's just force equilibrium. I said if I switch off this and I switch off this and I have force equilibrium, and force equilibrium means that the force on that must obviously be balanced by the sum of forces on all the other three sides. That's all. So this first equation is force equilibrium. This is just geometry. I put these things together and I can write it down as I've done over here. Okay? So the stress tensor defines now the force per unit area locally. So that's good, but it's unfortunately not enough because I still haven't told you what sigma is related to u. So I have a conundrum. So my equations have a variable which is the density, a vector variable which is the velocity, eventually I'll also have a temperature, although I'll go through this fairly quickly because I'm not going to tell you about any situations where we are not in the isothermal limit. So the problem is I have introduced a new variable sigma, and this new variable can be and will be, the only way to close the system is this new variable sigma must be some function of u, could be a function of density, and so on and so forth. Yeah? Is the question? Yes.
Take you a little step back maybe.
Sure?
The definition, you talk about the material derivative. So how do you define this partial? Because its shape can change also in
Yeah,
the,
of course.
the flow, right?
Yeah.
So you select some initial volume and then it can turn into something else.
Indeed.
And you're just looking at the math that gets them out.
Exactly. Exactly. So it's all, yeah. So now you're asking, and I'll solve the problem for you, probably not today, but tomorrow morning, where you're tracking the boundary as well. Okay? So for example, if I'm thinking about a wave on the surface of water, I have to track the boundary. And how do you do that? So that means you have to have some condition which tells me how the boundary is evolving. But as far as I'm in the interior, I don't care. But it's a very important point I'm making. Yeah, question?
Can I clarify one thing? The way you put it, basically, you use this equilibrium condition, assuming that there are no external forces, no acceleration. But I think this relation is also true when these forces are present.
Of course. And all I have to do is now this equation I have to replace by saying that there is a density times acceleration, mass times acceleration. That's it.
Right, but then it's not the density, it's the mass inside this thing. And
it's the mass of the tetrahedron, exactly.
And the mass goes to zero, and that's why it's applicable even when the...
Exactly, yeah, yeah. So I did this in the cheapest way, but I would have now one more term, which I have a volume times an acceleration, exactly, times the density. Thank you. Okay, so in principle, I don't have enough equations for enough unknowns because I have u and rho, but I've introduced a third unknown, sigma. And sigma could be a function of I don't know what. And depending on what kind of material you have, you will actually have dependencies on potentially all these questions, all these situations. So how do we deal with this? So what we're going to do is use invariance. What we're going to do is, well, in a fluid mechanical system, I must first of all have Galilean invariance. If I have Galilean invariance, if I move the entire fluid with a uniform velocity, I shouldn't expect to develop any stress. Right? It's just rigid motion. So that means that if I have a dependence of u, that's impossible. Purely on u, that's impossible. Because I change u, I add u, a constant, a uniform constant, and I will get a contribution. So sigma cannot depend on u. But it can depend on derivatives of u. Okay? And for now, I'm going to think about derivatives with respect to space. When you start thinking about polymer dynamics, you'll also see derivatives with respect to time. But today, I'm not going to tell you about that. That I think people will talk about, I hope. Okay? So if I think about derivatives in time, space, excuse me, and also, I'm not going to think about dependence on density. I'm going to tell you why, because in a minute, I'm going to separate out the dependence on density through this thing called the pressure, which I've not introduced yet. So it cannot depend on u. So I'm going to do what Phil did before, is to do an expansion, but rather than an expansion for a virial expansion for quantities as a function of density or concentration, I'm going to do it now for dependence on gradients in u. Okay? So sigma is a tensor, so I'm going to say, well, it can't depend on u, but perhaps it can depend on grad u. And it could depend on higher terms, higher order terms. If I keep the first term, then maybe I'll say, well, it could be a function of this grad u. Grad u is a vector, the gradient of a vector is a tensor, so I'm okay. There's a 2 tensor on the left, there's a 2 tensor on the right. In general, a 2 tensor related to another 2 tensor, there's a 4 tensor. Okay, I'm not going to go through the mathematics of this, but there's a problem. There's still a problem. And the problem is that the gradient of u, okay, the gradient of u is a tensor, a matrix if you will, and you know, I think from your course in matrices, that I can always decompose a matrix into a part which is associated with the rotation and another part which is associated with stretching. Okay? I also, so not only must I have invariance with respect to rigid translations, I must also have invariance with respect to rigid rotations. I don't expect to get a stress if I just rotate the object. So, in fact, I can't have a dependence just on grad u, I must have a dependence on the part which is not associated with rotation. And so I can only have a dependence on the symmetric part. Why is that? Because the rest of it, this quantity, okay, there's convention which says I can write down grad u like this. This quantity is related to, if you depending on your persuasion, spin or in fluid dynamics, vorticity. Okay. This quantity, by definition, so this is a matrix minus its transpose, so therefore its diagonal elements must vanish, and the transpose of this is equal to the negative of itself. So therefore, it doesn't have, so first of all, 3 elements are gone, the diagonals are gone. Transpose is equal to negative itself, that means instead of having 6 elements, you only have 3 elements, which are independent. Yes? Just by counting. Now, there's a miraculous theorem which works only in 3D, which says that this element, this matrix operating on a vector, is exactly the same as a vector operating on a vector. Okay? So, that's why I relate this tensor to this vector. And I'll come back to this again. But for now, all I want you to remember is that this quantity is associated with rotations. So I can't have a dependence. I can only have a dependence on the symmetric part. I can't have a dependence on u. I've dropped a dependence on rho. So what can I write for sigma?
So,
Question?
what physical property are we looking at to determine what if the variables will depend on?
Okay, so let me go back. Thank you for asking that. So I said that when we were in grade school, we were taught the difference between a fluid and a solid is that the fluid will respond to rates and change of shape, but it doesn't care about shape itself. And so if I think about that, then I'm going to ask yourself, so rates of change of shape are related to velocity. And so I wrote down sigma to be a function of velocity. But then I said, look, if I just move this fluid in a container rigidly, I don't expect any stress, any forces. So then I say, it can't depend on the velocity itself, it can only depend on differences in velocity, spatial differences in velocity. So the picture that I'd like you to have, and I'll give you a physical meaning in 5 minutes or so, because I'm going to actually give you an explicit formula and I'll tell you how to measure everything. But you understand that bit? Because I know that it depends on the velocity, but now I'm arguing that it can't depend on just some arbitrary function of velocity. At first order, doing an expansion of f of grad u, and remembering that I can't have a dependence on the rotational part, I must have a dependence only on the symmetric part. Okay? Okay, so I'm now ready to now write down, finally, after all this, the simplest form. Question, Leo.
Excluding sort of more structured fluids like
Absolutely, I said that, yes, I emphasized that right from the beginning. Yeah, I'm going to exclude it and I'm going to show you how to introduce structure.
You can have a rotation.
You have to have more dependent variables. Indeed. Absolutely. Okay. So now I'm going to tell you what the form is for this stress tensor, because I said I don't have enough equations. Sigma must be a function of u or rho. I've dropped this dependence on rho, I'll bring it back. If it's a function of u, I say it can only depend on the symmetric part. And here is my first constant. I'll give you numbers for it, but right now it's completely phenomenological. Okay? So you have a term which is proportional to the symmetric part of this quantity. So I should give you names. This quantity, you will see a lot. Sometimes called the deformation gradient rate. It's called the deformation gradient rate because the deformation will be the position. It's already got a rate because it's a velocity and it's a gradient. Or a strain rate, although people will often call the strain rate only the symmetric part. They won't talk about this. So this quantity is called the strain rate and this quantity is called the spin, and up to factors of 2 the vorticity. Okay? So, here is now the simplest relation that I can write, connecting the stress to the deformation gradient. We argue that it can only be a function of the symmetric part. And there's another bit, which is just constant, sorry, not constant, excuse me, but which is independent of direction. Okay? So, there is one more part. This is what I just introduced to you, and let me tell you about this. And again, I'm going to use a little bit of physical intuition if I can. Imagine that I have particles which are interacting with each other. The simplest molecular interaction is a central force interaction, okay, where everything is radial. So central force interactions, I have to give you one constant and I'm done. And indeed, there is one picture of a fluid like that, not this one. I'll tell you about that if I forget to ask me at the end. But in general, you can have central forces and non-central forces. So the first approximation, so this comes back to Leo's question in terms of structure, the simplest structured fluid that I can have is where I have two constants, one associated with central forces and one associated with non-central forces, and that's it. Okay? Equivalently, if you want to think about it in terms of geometry, then there are two kinds of deformations that I can have for any fluid blob. One associated with changes in shape without changing volume, and the other associated with changing volume. That's a geometrical view. Okay? And these two beasts essentially correspond one to each one. This is associated with contributions to changes in volume, and changes in volume, it's a scalar, will lead to forces which don't depend on direction. If they don't depend on direction, you must have it multiplied by the identity matrix, and this bit is everything else. Okay? Alright, so I want to now unpack this also. Let me unpack this a little more. I've written it down in a way which hydrodynamics texts will write it down as having two parts to it. So I've introduced this viscosity with numbers in a little bit. I have to unpack this. One is a contribution which is, if you like, a thermodynamic pressure. The thermodynamic pressure associated with an equation of state, which tells me, for example, that I have interactions between particles, they are dependent on the density, they are dependent on the temperature, they're dependent on concentration, all that sort of thing. And then there is another part which is associated with motion, which will occur only in the presence of motion. So this, if you like, is a thermodynamic contribution. It's done, this separation is there purely because I have to have different pieces of physics associated with each one of these. And the rest of it is associated with a dynamic bit. The fact that I've written down this new parameter minus 2/3 is a detail which I don't want to go into. It's associated with just trying to figure out how to do the isotropic and the non-isotropic bits. Okay? But the important thing is that there are two constants. Constant 1 is mu, and constant 2 is zeta. It's a two-constant fluid. If you like to think of these two, this is associated with the central force bit, and this is associated with the non-central force bit. The changes in shape. Okay? Now we're done, because if I tell you mu, and I tell you zeta, and I tell you p, so I've introduced one more, and then I'm done, because I have enough equations and enough unknowns. Okay, now I just stick this sigma into my equation of motion. Now I've written that down again in Eulerian rather than Lagrangian. So this is my acceleration in an Eulerian frame, and I stick sigma, take the divergence of this, and I get now 3 terms. I put in a 4th term if I have an external body force, for example, gravity, or if I'm in a non-inertial frame, effects of rotation, and so on and so forth. So, what are the meanings of each term, of these terms? And they look horrible, but what can I say? Acceleration, or mass density, density times acceleration is balanced by all the interactions in the fluid, and then the external body force. Interactions in the fluid have an isotropic part from pressure, which itself has 2 bits to it, the thermodynamic pressure, which I've separated out over here, and the associated pressure because of changes in the volume of the fluid because of dynamics, because of motion, and then this quantity. Okay? So if I have a gradient over here, I'll have a Laplacian. This is now the equation of momentum, but for balance of linear momentum. Now I have a problem. Okay? I don't have point particles, and if I don't have point particles, I have to also worry about the fact that if I have an extended object, I have to worry about the fact that they can spin and they have orientation order. So what do? I have to now understand how to essentially conserve momentum, angular momentum, not just linear momentum. For an unstructured fluid consisting of point particles, which have no microscopic orientation, conservation of angular momentum is exactly equivalent to saying that the stress tensor is symmetric. Okay? In fact, what I'm really telling you is that these two quantities are just proportional to each other. Because otherwise, I actually will have a difference. And let me show this to you through a picture. Okay? So imagine in 2 dimensions, and I'm doing this very deliberately again on the phenomenological scale because it's an alternative view, which I think is quite useful. Imagine it's a 2-dimensional picture, and here is my little blob. It's a square blob. It doesn't have to be square. It has dimensions delta x and delta y. And I look at all the forces that the environment applies to this, and through Newton's third law, then this applies on the environment. So I could have forces in the normal direction to the faces, or I could have forces in the tangential direction. Okay, and the way of drawing things is that if I draw a force in the positive direction, it's associated with the normal in the positive direction. If I draw a force in the negative direction, associated with the normal in the negative direction, the sign is still positive. That's my little element. And I could have then, this is the 1 direction, this is the 2 direction, so sigma 1, 1 is the force in the 1 direction on a face which has a normal in the 1 direction. This is the notion of stress that I told you. Similarly over here, sigma 2, 2, there could be a variant in between these two, difference between these two, and sigma 1, 1, and then this is sigma 1, 2. The normal in the 1 direction has a force in the 2 direction, that's a shear. This is sigma 2, 1. The normal in the 2 direction has a force in the 1 direction. And I'm now going to write something, and I'll try and explain it to you. First of all, force balance on this element implies that sigma 1, 1 must be the same in the absence of body forces, right? Because otherwise this thing will accelerate. So there are no body forces, so force equilibrium says that the sigma 1, 1 must be the same, similarly in the vertical direction. Also, force balance says that this force, if I now for a minute forget about translational degrees of freedom and only worry about rotation, so let me simplify things just for clarity. Now I think only about rotational modes. This object, sigma 2, 1, has to be the same as this force, and sigma 1, 2 has to be the same as that force. Because if it wasn't, I won't have force equilibrium. Everybody with me? Well, what about torque equilibrium? So torque equilibrium says that this quantity, this force and that force, want to essentially make it rotate in 1 direction, and these 2 forces want to make it rotate in the opposite direction. And if they don't balance, you can just see this immediately, it will start to spin. Which means that sigma 1, 2 is a very simple setting, had better be equal to sigma 2, 1 if I don't have any microscopic orientational order which I have to account for. In my last lecture on tomorrow afternoon, I'll tell you about magnetic fluids where that's not the case, where I can have dipoles, and these dipoles have their own orientational degree of freedom, and in addition, you have globally these dipoles can be moving in a rotational field. And then omega, the spin, and the deformation rate gradient are not the same, which means I have a separate equation that I have to handle associated with angular momentum balance. But for an unstructured fluid, some saving grace associated with the fact that I don't have to worry about it. Okay? All right, so do I want to tell you about, I really am not going to solve any problems associated with heat conduction and convection. Maybe I will tell you quickly about the fact, well, I have to also worry about temperature, heat, entropy, energy, all these kinds of things. And you have to write down an equation for conservation of entropy or non-conservation if I have sources and sinks. Again, I have the material derivative. Okay? Rho is the density, S is the specific entropy, the entropy per unit volume, T is the temperature. So the left side is the derivative, the advective, the material derivative of entropy, and it has two sources really. One is conduction, heat conduction. So if my fluid has a finite conductivity, then of course I have a diffusion term, the conductivity multiplied by the Laplacian of the temperature. And now, because the fluid can dissipate energy, I also have viscous work. And the viscous work has two parts to it. One associated with this bit, the anisotropic bit, and the other associated with the isotropic bit. So intuitively, I can do work by essentially squeezing and unsqueezing the liquid, changing volume, and not changing shape. And then I can do it by changing shape and not changing volume. And those are the two contributions that you see over here. Okay? So one bit from here and the other bit from here, associated with changes in shape without changes in volume, changes in volume without changes in shape, and finally okay, so with that, I have, oh, and I said that, but let me, I didn't say that, I said I would. I must also tell you about the thermodynamic pressure, and that could be related, for example, to the density and the temperature, and then we have enough equations, because we have 1 plus 3, 4 plus 1, 5 unknowns. I have mass conservation, which is one equation. I have momentum conservation, linear momentum conservation, which is 3 equations, and I have the temperature equation. Okay? Which, if I know how to relate entropy to temperature, which I do use in thermodynamics. Okay, still not enough, because I told you we need boundary conditions and initial conditions. So I have to specify the velocity, I have to specify the temperature, and then I have to specify either the velocity and or the pressure. I can't specify both, and simultaneously for entropy. That's for boundaries which are open, where fluid is leaving, or heat is leaving or entering, or I prescribe a pressure. What happens if I have rigid boundaries? So this is the nastiness of fluid mechanics. Most of the nastiness of hydrodynamics is associated with an empirical fact. It's an empirical fact because it was just assumed in the 19th century. And recently, over the last 20, 30, 50 years, has been shown not to be always true. Many situations where it's not true. The assumption in the 19th century was that, in fact, fluids essentially don't slip on a rigid boundary. Many experiments show that. For example, if I introduce a dye, and the dye in the bulk will get advected, and the dye on the boundary will essentially stay there. But this is a very hard condition to essentially deal with, and again, I will do this in the context of examples. But let me tell you first where it fails. In fact, it fails in all interesting problems in soft matter. When the density of the gas or the fluid is very low, that means the mean free path starts to become very large. That means the continuum theory itself is starting to break. Again, just like what we heard previously, when I have to worry about effects where density is small, in fact, I will have slip. Another example where this fails, very simple example, is if I think about a bathroom sponge and I have flow past it. Okay? Obviously, some fluid is seeping into the sponge as well. So if it is seeping into the sponge, what is the boundary condition on that porous interface? In fact, you have slip. If you go deep enough into the sponge, you don't have motion, but on the sponge boundary itself, you do have motion. So it will fail at a structured interface, any structured interface. If I have a hydrophobic surface, where I may have a small amount of vapor, or an interaction between the fluid and the substrate, which is non-trivial, again, you start to fail. A beautiful place where it starts to fail is on your window pane, where if I have a drop of liquid, which is moving, obviously, if the drop is moving somewhere, it's slipping, because the drop initially was at one location, later on it's another location. That means where does it start to fail? Well, it fails first at the triple point. The triple point corresponding to, if here is my window pane, here is my drop of water, and the drop of water is starting to move. Clearly at that point, and as a consequence at all other points, as the drop starts to move, this is vapor, this is liquid, this is solid. If I have no slip, the drop can't move. The drop moves. So there's a problem. Question?
What if it rotates like a wheel on?
Very good. Yeah. You can indeed get it to work. So an exception to that rule, as you point out, is what would happen if a drop rolled without sliding. Okay? And we worked out exactly what happens in that situation, because now you can go get away. You don't have to violate the no slip. You have no slip, but you have now rotations. Okay? So now you can ask the question, what happens if I'm close to perfect rotation, but not perfectly? rotating like a rigid body. And then I have to come back. So there's only one limit, perfect rotation, where it won't work. Anything else, you have to essentially slip it into. But indeed, there are examples of that. Mercury on glass, to a first approximation, looks like it's rolling. If I have a glass surface which is microstructure, very rough, then the drop of liquid is in contact mostly with air, because it's suspended on a bed of nails, like a fakir, if you will. So that also can almost roll. So there are situations like that, but in general, the generic picture is you have a problem. Okay? And how do you deal with that? Well, a way to deal with that is to essentially throw away this boundary condition, and replace it by a kludge, and this is the kludge. Replace it by this condition: U plus beta times du dn on the boundary vanishes. Okay, where n is the normal to the boundary, and by dimensional analysis, if u is a velocity, this is a velocity, this is a direction, so this must have dimensions of length. So when beta goes to 0, you recover the condition, and beta is not 0, it starts to slip. But it's a kludge. It's just the simplest expansion of the boundary condition. Just like we expanded the stress, I just expand the boundary condition in powers of the velocity gradient. Constant, no dependence, first dependence on the velocity gradient. Okay, so that's the case for rigid boundaries. What happens for free boundaries? Question?
How do you fix this data?
Okay, very good. So, two ways. If you were an experimentalist, you measure it. But then you've got to start worrying about how does it change when you go from one material to the other. If you wanted to calculate it, you've got to go back and actually start thinking about this joining or disjoining pressure, which says that microscopically there's an interaction between the liquid, vapor, and the solid on a scale associated with a few atoms in size. And then I ask, what is the consequence of that? And the consequence of that tends to be, in physical terms, that depending on the stress at the interface, the liquid contact line will or will not move. And the rate at which it moves is a function of the microscopic parameters and the macroscopic forcing, for example, that due to gravity. I can't give you a more simple answer than that, because it's still the subject of a lot of debate. How do you calculate it for a microstructured surface? What happens if I have roughness? What happens if I have a soft substrate? What happens if I have a hairy substrate where the hairs can deflect? We don't really know. There's a lot of things that can be done and should be probably done over there. Question?
Can you say that there is some kind of singularity of triple point?
Yeah.
And solve the system and just replace it with some...
That's exactly what this is doing for you. Okay? Indeed, what you're saying is that, so for the others, so the idea is that, look, the thickness of the fluid is going to 0 as I approach the critical line. So in principle, if I'm thinking about velocity gradients, the gradients would be all associated with direct gradients perpendicular. So if the thickness is going to 0, then the gradient is starting to diverge, because the thickness is going to 0. So that means the stress is diverging. And if you say, well, you can't allow the stress to diverge, some new piece of physics kicks in. That new piece of physics is what I was telling you, associated with the microscopic interactions. Indeed. Okay? So this would be an empirical approach. That would be a pure hydrodynamic approach, which said, look, I have a problem. It turns out you get a logarithmic singularity. So it's a weak singularity, and then you can essentially get around that by putting in some piece of physics. What about free boundary? Yeah, Leo?
Yeah, I was just going to maybe comment on, so the earlier comment about the antisymmetric part of the stress tensor vanishing. I mean, it's a little bit, when you make an argument for a finite element of fluid, you can imagine that instantaneously you could have some anisotropic part of the anisotropic part of the, not anisotropic, but antisymmetric part of the stress, and it's balanced by the moment of inertia of that.
Good, yes. So that would basically say that the difference between, you're absolutely right, the difference between sigma and sigma transpose will then drive the rate of change of the spin. And that will essentially make these two not be identical, precisely. And by saying sigma is equal to sigma transpose, I'm saying that the relaxation of rotational or a degree of freedom is much faster than the translation degree of
It's just
freedom.
not a hydrodynamic moment, but it's really there.
Indeed, exactly. Okay? All right. what happens if I have a free boundary? Like, for example, the boundary between liquid and air here, or in a drop. So this comes back to the question that you had, I think, earlier. What do? What is the boundary condition? So what's the definition of a free boundary? Okay. The definition of free boundary is it's free, but is it free of everything? And the answer is, the first approximation, not quite for a liquid, because I have interfacial forces which are unbalanced, or could be. Interfacial forces, excuse me, which would give rise to a normal interaction which is potentially unbalanced. So if I think about interactions between molecules due to collisions, due to whatever, I don't really care, then just because of the geometry as I approach an interface, there's a problem. Okay? And if I now ask, what does that lead to? What does that unbalanced force lead to? Well, again, I can use a Taylor series argument, a symmetry-based argument, which says the force, so the force on this side has to be different. The isotropic part, if I'm thinking about something which is stationary, there is no anisotropic part. So the pressure here has to be different from the pressure over here precisely because of a curved interface. It can't depend on the location of the interface. Okay? Because if I just move the interface, it can't depend on that. It can't depend on the orientation of the interface. So the first term that comes in must be the curvature. Again, the symmetry argument, but again, you can go back and calculate microscopically. So the first term that appears is proportional to the curvature. And this equation tells you the relationship between, this is in the general case, let me start with the static case, the difference in pressure between the inside and the outside associated with the curved interface in a fluid with no structure at all, but just a density, sharp density interface. Pressure difference is proportional to the curvature, and again, it's proportional to the curvature, and the left side is the pressure, a force per unit area, the right side is the curvature, which is a 1 over the length scale. So that means this quantity has to be a force per unit length. So that a 1 over the length times the force per unit length is the pressure. So again, I've constructed, just phenomenologically, a change associated in the stress associated, or isotropic part associated with an interface. The more general equation where I have a contribution not just from the pressure but also due to the flow would just replace the left side by the stress projected in the normal direction and the difference in the stress between these two directions, between these 2 points on one side and the other side is gamma times kappa in the direction of the normal. Okay? And again, I'm simplifying things enormously because I could have gradients in the plane. I could have gradients, for example, of molecules, and I think we're going to hear a little bit about that from Michael, perhaps in the context of surfactants and things of that sort. And I could now have much more complex interactions, not just an isotropic part, but an anisotropic part. This curvature, in this one-dimensional case, is very simple. It's just the second derivative of the displacement. In the more general two-dimensional case, curvature is really twice the mean curvature. All right, so I'm now going to put numbers. Okay, finally, everything's now in place. I've got boundary conditions. Question?
So these are the two sort of extreme. Do you ever deal with the boundaries of two co-moving fluids?
Absolutely, yeah. So yes, you can. And then what would I have? I would still have, so if I have two fluids that are moving relative to each other, on the boundary between them, the velocity of particles must be the same whether I approach it from here or whether I approach it from there. And as long as I don't have sources or sinks of force, which means I don't have dipoles or quadrupoles or monopoles, then the stress must also be continuous. So what I'd have to do is to just replace these two conditions by not saying it's equal to 0, but the jump in the velocity, the jump in the stress across the interface vanishes. Okay? Yeah, indeed. So it's, and there's a zoology of boundary conditions in between where I slip a little bit and so on and so forth, which I sort of indicated over here, and then I have curvature. You can spend, many people spend their lives on that. Okay, so numbers. I now introduce 3 parameters in the fluid problems, in the simplest setting of all fluid problems associated with an unstructured fluid. A density, we're going to ignore that from now on, in fact, because it's going to be incompressible. A viscosity, if it's incompressible, only one viscosity because the dilatation of viscosity. The zeta vanishes because the divergence of u is equal to 0. And a surface tension. Those are intrinsic parameters. And then you pick a system which has a characteristic length scale, perhaps. and a characteristic velocity scale or a pressure. I've chosen velocity over here, which is driving things. Okay? So we have these three quantities. These two obviously are problem dependent. These three are fluid dependent. So I want to give you some intuition for those. We are basically telling you about how to measure them. Okay? Density I won't tell you about because you can weigh, presumably. Not easy to do accurately, but you can do it. What about viscosity and surface tension? So viscosity, the easiest way is to essentially think of what you do and what you call slipperiness. Okay. If the naive person on the street will tell you this fluid is sticky, this fluid is slippery, and what they're really telling you about is a complex combination of viscosity and adhesion. But to a first approximation, if all I'm doing is moving two plates parallel to each other and keeping the distance between them, the resistance to that displacement, or the rate of displacement, the velocity, is a measure directly of viscosity. And that's what is used classically, in fact. So I probably should have started here, but here it goes. Where I take a plate, I move it a little bit to another plate, I measure the force per unit area on this plate, keeping this plate constant. That force per unit area I call the stress. I know the velocity at which I'm moving it, and so I need to relate the stress to the rate, and the rate in this case is just the velocity divided by the thickness. So there's a name. In fluid mechanics, there's a name for every problem. Usually two names, because a few people contributed a lot, more or less simultaneously. And this kind of a device, this kind of an experiment, is called a Couette device or a Couette flow. And because it's a planar problem, it's called a plane Couette flow or a plane Couette device. Okay? So that's stress. That's a velocity divided by a length. So that's a rate of change. This is exactly consistent with your intuition that fluids respond not to changes but rates of changes. Velocity over length is 1 over time. And you can measure it in this picture, in this simple device. You could measure it by having a cone coming close to a plate and spinning the cone. Why do you use a cone? Why can't you just use a flat disc?
Because the shear is constant.
Because the velocity, the linear velocity is proportional to the radius, and the linear velocity proportional to the radius, therefore, if I don't change the gap appropriately, I will not have du dy be a constant. Okay, so that's why you use a cone. Or you could just drop a ball inside the fluid, and if you drop a ball, you can essentially have a balance between gravity and viscous forces. Okay? And if you can do that in the limit where the ball is not moving fast, which I will tell you about in the next 5 minutes, then you can calculate it. And I'll tell you about this formula also next time. Okay, numbers. The viscosity of air is 10 to the minus 5. What are the units? Pascal second, because this quantity has dimensions of Pascal, force per unit area, Newton per meter squared, and du dy has dimensions of 1 over time, so mu has dimensions of Pascal second. But this is a meaningless number for me unless I compare it, and so I want to compare it with two other common liquids. Water is 10 to the minus 3, and honey is 1. That's the way I remember it. Honey is 1,000 times more viscous than water, and water is about 100 times more viscous than air. That's the way I remember it. Again, same question that you asked before. This is phenomenological. I can measure it. Can you calculate it? And the answer is yes, you can. You can calculate it using a kinetic theory. And a crude way to calculate it is to ask, what does it mean? Okay? Physically, what this mu is characterizing is the rate at which momentum is transferred tangentially. Okay? And I think about the energy scales of the problem, which is typically associated with kT. And I ask about the mean free path. And then if I have kT over m, which is a velocity squared, and I put the numbers in, I get a velocity, I get a mean free path, the ratio of those two is approximately in the right ballpark for dilute gases. Question?
So what is the microscopic interpretation of the rotation viscosity?
Thank you. I said before, I repeat, it's changes in volume. So this allows you to change shape without changing volume. Now I can ask, can I do an experiment where I can change the volume without changing the shape? Imagine a sphere, which is essentially pulsating. Okay? For simple liquids like water, it's almost incompressible, and I don't care about the dilatation of viscosity. A beautiful beautiful example of where the dilatation viscosity is very important is in a bubbly fluid. Okay, like soda, fine, with bubbles which have already nucleated. Now I'm moving, but this is a more complicated fluid because it's got two phases. But the microscopic picture is changes in volume. Fundamentally, geometrically, everything that we are doing is trying to do two things: characterize the translational modes and characterize the rotational modes. That's it. That's all of fluid dynamics. Everything else is bookkeeping, and we just can't solve the equations. Okay, so how about surface tension? How do we measure surface tension? Again, you could do it empirically, or you could use microscopic theory. I'll just tell you about the empirical method. There are many. Two methods. One is to just have a drop hanging from a tube, okay, and ask what is the size of the drop just before it leaves, or at some, for a case where the angle that the contact line, this quantity that I told you, this is a liquid, this is the vapor, this is the solid. This is something which is amenable to measurement. So if I measure the contact angle, I know the size of the drop, so I know M, I know G. I just do a force balance. The only contribution that I don't know is gamma. And think of gamma as a line tension. Gamma is essentially the force per unit length, which is operating on this rim in the vertical direction. It has a component which, of course, is there in all directions, but because of symmetry, the only contribution that it ends up having, which is non-zero, is the vertical one, or the up and down. The horizontal one just cancels out because of circular symmetry. So that's unknown. You can measure that, and you can calculate everything else and measure gamma. Numbers. Water has a surface tension. Air has a surface tension of about 0.07 newtons per meter or Pascal meters, and alcohol, another common liquid, is about a third of the surface tension of water. Okay. All right. So we now have the numbers. We have the equations. I can tell you about the limit that we will now focus on. The incompressible viscous liquid, so divergence of U is equal to 0. I'll never really worry about the heat equation, even though I've written down for completeness. And this is my Navier, this is what's called the Navier-Stokes equation, written by Navier and Stokes in about 1840 or so. I already introduced the vorticity, I'm using a different notation. In the incompressible inviscid limit, so the viscosity goes to 0. So all interactions in the fluid are purely due to pressure. Okay. And now this is a problem in geometry, really. It's not a problem in some sense in physics, because if it's incompressible, I don't have an equation which relates pressure to density. I don't have shape changes because they're gone, or I don't penalize them. So all I'm doing is tracking the isotropic part of the stress as a function of space and time. And of course, the velocity. So the physics, in the sense of parameters, has essentially disappeared. These, therefore, these two first equations are beloved of mathematicians because they're really just tracking what happens to fluids as the velocity and the pressure move around, advected or not.
But the pressure you don't input. Pressure is something that will adjust.
Indeed. Yeah, exactly. So the pressure adjusts so that that condition is...
You just adjust to get rid of longitudinal part of the velocity.
Precisely. Yeah, exactly. That's why I said these two equations together. The second equation is the constraint which forces the pressure to do whatever it's doing. Exactly. And the entropy equation, it just becomes trivial because entropy is conserved. I don't think I want to tell you what inviscid and compressible flow because this is a whole course on itself. So I will finish by telling you a different approach now. I'll stop and tell you a different approach. Okay? So what did we use? We used balance laws. Balance of mass, linear momentum, angular momentum was sort of trivial. And then we used symmetry and invariance to deduce the relationship between stress and strain rate. You could have not worried about that initially, you could just go all the way. And recently, go all the way using symmetry from the beginning without introducing the balance laws themselves. And recently there's been a lot of work in trying to argue for a hydrodynamic theory of other things rather than just inanimate physical objects. Could be robots, could be people, could be fishes, birds, bees, God knows what. And there's a huge, growing interest in trying to ask whether or not you can do this. And by no means is it obvious that you can answer all questions using this approach, but some questions perhaps you can. And so here is an approach, which is borrowed from a series of review articles by these people over here, Toner, Tu, Ramaswamy, although the antecedents go back quite a bit. Mass balance, if I don't have things reproducing, remains what I told you before. And now, rather than write down momentum balance, I just write down a Taylor series expansion. Okay, another Taylor series expansion for the velocity, but now I have to have some control, okay? Some hygiene. And the hygiene that these authors posed for themselves is, let's stop at terms which are second order in space, and let's stop at terms which are cubic in speed, and write down all the possible terms that I possibly can. Okay? So I won't even call this a momentum balance equation. Call it what you want. It's just a balance for, or an equation which tells you how the velocity evolves. Leo, you have a question?
I just want to, sorry to interrupt, but we're a little constrained on
time.
On the
okay.
time. Yeah. So I was wondering just what the.
This is it. This is the last slide. Yeah. Okay. So here is, I'm sorry you can't see because I indicated in blue. Here is all the terms that you can imagine writing, where you have one derivative in time velocity because that's an acceleration, and then all possible combinations of gradients in velocity and velocity itself up to cubic order. So first derivative, one gradient. There's one equation, one term is one gradient, a second term is one gradient, and a third term. Those are the only three. You can check. And the terms with two gradients are these three: Laplacian, u dot grad square, and grad of divergence. Those are the other three terms. And I have, because I'm no longer Galilean invariant, I'm not said anything about Galilean invariance, I can have a term which is proportional to u. And finally, if I go to cubic order, I also have a term which is proportional to u dot mod u square. I don't have a term which is proportional to u times mod u because that's not analytic. Okay? That's it. Those are the equations. That's the equation. And there's no physics. There is no physics of any kind in the sense that I'm not invoking balance of forces. I have invoked locality, as you said, or these people have invoked locality, but otherwise, this is it. Okay? This is, again, a symmetry-based approach where we have not used the balance laws, at least explicitly, and because we didn't write down the considered equation, we simply wrote down an evolution equation where you have all these constants and they have to be determined somehow, empirically, experimentally. No, not clear. Okay, so for tomorrow, I've shown you the equations and I have to show them to you once. Now you will only see different bits of the equation where I will essentially ask what kinds of phenomena can you explain, because these equations, either this one or the one before, first of all, are nonlinear. You have this u dot grad u term, which is the nightmare that haunts everybody who goes to hydrodynamics. And secondly, you have many terms. You have 4 or 5 terms. And it's very, very unfortunate if all those terms are of the same order. And so, if they're not all the same order, then the first thing to guess is at least 2 are of the same order. And so there are many ways of choosing those 2 and many ways of choosing boundary conditions, and that's where the zoology of hydrodynamics starts. And I'll tell you about that in 2 lectures.